Yeah, my name is Sanchuan, and this is a joint work with my advisor, Professor Zhiqiang and Professor Yinqian Zhang. Our paper title is Controlled Data Races in Enclaves. Basically, we investigate the data races in the enclave scenario. We try to perform attacks and detections. Okay, so everyone here knows the TEE, and we mainly focus on the Intel SGX. So the Intel SGX is a protected memory region with its confidentiality and integrity protected. We can see at the bottom is a basic structure of the Intel SGX scenario. And we know the Intel SGX is vulnerable to side channel attacks, such as controlled channel attack. But a natural question is, how about other classic attacks? So here in this paper, we investigated the data race in the enclave scenario. So you can see we magnified, and you can see within each enclave, there could be multiple threads. And in our investigation, we found that the data races in enclave is different. It has two reasons. The first reason is that the data race in enclave can be controlled. So you can see in the classic scenario, you have two threads, and one of the threads is read and write, another is write, and they have a data race. And this kind of data race totally depends on the thread scheduling of the system, so it's non-deterministic. However, in our enclave scenario, the data race can be controlled by the malicious attacker outside the enclave. You can see there's a box with the yellow box is the enclave, outside is outside the enclave, and everything outside is untrusted, including the operating systems and other firmwares. But inside the box is the enclave. So we have two threads. One is victim thread, another is attacker thread. They both enter the enclave, and then they have some shared memory access, and they have a data race. However, this one can happen if you have these three steps. You can make it deterministic. The first step is controlled thread creation. So we know in some trusted execution environment, like Intel SGX, they try to make the trusted computing base, the TCB, very small. So a lot of libraries, a lot of functionalities are moved outside the enclave. So for example, the thread creation is outside the enclave. So that functionality can be used by the attacker to start a new malicious thread. And the second step is the controlled concurrent enclave call. So after the malicious attacker creates the malicious thread, he can make an enclave call and enter into the enclave. And the third step is a controlled synchronization point. So when we try to race to the synchronization point, we can send interrupts or page faults so that they can reach at the exact point. So this makes the data race in the enclave deterministic. Another difference in the enclave scenario is that data race in enclave has unique thread interleavings. Here we have an example program which we have two enclave calls, eCall0 and eCall1. So I would like to emphasize this one was intended to be a single thread program. So that the intended thread interleaving is only one thread. And you call the first function first and then the second function second. Since there's only one thread, there's no data race. However, in our unintended thread interleaving, the malicious attacker can create a new thread and have the data race. So for example, you can race at the shared variable, which is data corruption. Right? The second scenario is you can also corrupt the pointer, right? So here in this example, we try to corrupt the shared variable called the global counter, change its value in the victim thread so that the victim thread will jump to another place. And we call it control flow diversion. So based on these two observations, we know the thread, the data races in the enclaves are quite different from the normal case. And based on that, the data race detector is also different. The data race detector in the classic case cannot detect those interleavings, because those interleavings only happen when you have this kind of thread model. You consider the operating system is malicious, and they create a new thread interleaving that the programmer never know. Okay, and based on these kind of things, we have two things. One is the attack, another is the detection. For the attack, we first pin those two threads, the victim thread and attacker thread, to the CPU cores. So here in the example, we pin the first one to the first CPU and second one to the second CPU. And then we send the APIC timer interrupts to those two CPU cores to control their execution. So we have two kinds of interruptions. One is a longer interval interruption, which makes single steps. That means we observe where the program is. And the second one is a shorter interval interrupt, which we can stop the thread execution. When both those two threads reach to the reaching point, we send the shorter interval interrupt to stop them from further execution, and then they have a data race. Okay, and then the second part is the detection. In our detection, it is a static analysis tool. Our static analysis tool is based on the lockset analysis algorithm. So it has two components. The first one is the shared variable analysis. Basically, you have an enclave binary, and you look at the binary and find out where is the shared variable accesses. Is the variable access is a read, or the variable access is a write. And the second component is lockset analysis. Lockset analysis is you look at the binary and find out all the shared all the logs, all the synchronization primitives like logs and ones, something like that. And then you run the lockset detection algorithm. So there are some details for the first component. We analyze the global variable, heap variable, and stack variable to see all the shared variable accesses. Second component, we analyze the logs in the binary. So in the binary, there are several kinds of logs. One kind of the log is off-the-shelf logs. That means it is provided by the API. And the second one is self-defined logs, like some user will use some instructions like exchange to define their own logs. We can also detect that kind of self-defined logs. And after we get the shared variables and all the logs, we run a liveness analysis and we run lockset-based data race detection. Okay, so for the data race detection algorithm, we have some details. That detection is based on lockset algorithm. First one is the lockset, and another is lock acquisition history. Where we need the lock history, because sometimes even though two accesses do not have common lock, they still cannot race. So this is one example. The line 6 and line 14, they don't hold a common lock, but they still can have some cannot have some data race because of the history. For example, the first eCall will lock on the mutex 1 first, will acquire the mutex 1 first and then release. But the second one will also acquire mutex 1. So these two cannot happen at the same time. And for the evaluation, we evaluate our detector on 4 SGX SDKs, and we detect many, about 100 data races. And for the SGX application, we evaluate 8 SGX applications and we detect about 1,500 data races. And there are some interesting cases. One is CVE 2020-5499, which is a Baidu Rust SGX SDK, which has enclave ID race. That means when you start the enclave, you can have two enclave with same ID. And this is malicious, and the severity is 9.8 out of 10. And we also have 4 interesting cases. One is de-randomizing PRNG. There's a data race on the random number generator Cs in one SDK. Another is changing callbacks. So there's some function pointer data races. You can also change the control flow. And the case 3 is replacing the network. So there's some neural network application in the SGX, but their network result has a data race. And the case 4 is some certificate. In some SGX application, even their certificate has some data races. And we compare our work with the related works. There are several dimensions. One is at the beginning, maybe 1970s, it is a distributed algorithm, and later they go to the practical data race detection tools. Another dimension is happened before and the lockset. Our detection is lockset-based detection. And the third dimension is the target. Other detectors based on the detecting the source code, like a Java source code or C source code, but our detector detects on the binary only. And the last dimension is dynamic and static. Our analysis technique is static, and others are some of the dynamic and some of the static. And to sum up, we propose and investigate some attack and detection in the data races in Enclave. And yeah, we are open source, and with that, I would like to take any questions. Thank you.